All right, significant figures. There's a lot in here about this. First of all, exact numbers. Exact numbers, we don't have to worry about significant figures because they are exact. We don't have to worry about any kind of including this into calculations as far as how many numbers there are. Any of you that have had significant figures knows what I'm talking about. If you haven't, I'm going to keep repeating myself about exact numbers, how they don't really affect much in our calculations, okay? But what I want to talk about is a concept called certainty. Okay, notice here it says when a number is determined by counting, the number has no uncertainty. Like if I tell you there's 21 people, there is exactly 21 people. There's no uncertainty about it. Okay, uncertainty comes in when you talk about measurements. Okay, so when you talk about a measurement, you talk about uncertainty. If you look on this slide, they actually talk about it. That unlike numbers attained by counting or by a definition, like a definition is, you know, 1 dozen equals 12 eggs. That's a definition. That's exact. Measured numbers have some degree of uncertainty. Okay, they have some sort of error associated with it. So when you report a number, you have to tell the reader information about that uncertainty. So if you measure something and you measure it at 16.1 centimeters, all right, you always have one number of uncertainty. So in this 16.4, I know that the 16 is absolute, but the 0.4 is uncertain. It could be 0.3, it could be 0.5, it just depends on the person who measured it. Okay, when I read this number 16.48 centimeters, the 16.4 are certain. This number is uncertain. So is it 8? Is it a 9? Is it a 7? It's somewhere in that range. I am not certain about it. Okay, let me give you a perfect example that I like to give. Let's say I have two different rulers. Okay, one ruler has this type of measurements on it. Okay, another ruler I got was a little more expensive because it's got a little bit more lines on it. All right, I don't have to, I'm not going to keep going. So imagine I have a piece of string and I measure the string. Okay, and I want to report what this number is. Okay, so how I would report this number, so in your mind you might be thinking, you know, like 2.5 or 2 3/4 or whatever. Okay, well, those aren't totally correct. The answer is 2 point and then one extra number. Okay, I am certain about the 2. It's between 2 and 3, so I know it's 2. It's the next number. Is it a 5? Maybe it's a 6. Probably looks like a 5 or a 6, right? Maybe a 7. I doubt it's a 4. Maybe a 7. Maybe. Probably closer to 5 or 6. But what's the point? I'm not certain. This is my uncertainty. So when I report this number, I can't say 2.53. Okay? Why can I not say this? Because now I have two uncertain numbers. If I am not certain about the 5, I sure am not certain about the 3. I have no idea what that number is. Okay? Because I don't even know if that number is right. That might not be a 5. That might be a 4. That might be a 6. That might be a 7. Okay? So this is not how you report numbers. So in lab, this really is useful in lab because we'll be taking a lot of measurements. In lab, you have to make sure you know the uncertainty in your equipment. Okay? So let's do the same thing, but this time let's use this ruler. Okay? And that's where it is. Oh. See if you can come up with a value for that. All right? Give you 3 seconds. Okay. Hopefully you said 2.5 something because I am certain about the 2 and I'm certain about the 5. I got the 2. This is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6. It's somewhere between 2.5 and 2.6. So I know the 2.5, but the question is, what's the next number? Is it a 5? Is it a 6? Is it a 7? Is it a 4? I am not certain about this number. I am certain about this, but I'm not certain about that. Okay? So that's fine. All these answers are correct. You can report as 2.54. You can report as 2.55. You can report 2.56, so forth and so on. Okay? You can report as any of those. Obviously, you want to try to get as close to it as possible, but I can't report it as 2.553918, right? Because I am not uncertain here, so none of this is even has any relevance whatsoever. So that's what uncertainty is. And this concept, the topic of this is significant figures. That's going to help us figure out what the uncertainty is in the number. Okay? So we just talked about measured numbers. So it's really the measured numbers that always have one uncertain digit. Okay? So significant figures are digits that convey the precision in which a number is known. Several rules can be used to assess which numbers are significant in a measured number. Okay, so if I give you a number, 0.032, let's say 3120, okay, there's a lot of information in this number. Okay, first of all, this digit right here is my uncertain value. I guess technically it's both of them, because is it a 19, is it 21, is it 22, is it 18? I mean, it's really that number right there, okay? But there are 4 significant figures in this number, and we're going to talk about how you know that, okay? So, first of all, any non-zero number is significant. There's 4 rules. There's 4 rules, okay? It's really the zeros where things get a little weird, okay? But if you have a non-zero number, they are significant. So in this example, I know at least 3, 1, and 2 are significant. I'll use this number as an example because it really has a little bit of everything in it. Okay. Next one, zeros. Zeros are really the weird part. Zeros between non-zero digits are significant. I don't have any here. Notice these zeros are at the beginning of the number, and this zero is at the end of the number. I don't have any zeros in the middle, but if I had a zero in the middle, it would be significant. It's important. So like this number has 5 significant values. Every single number is important. Okay, this has 3 significant figures. All right, if I had 0.03000010112, well, guess what? All of these zeros between the between the non-zeros are significant. Okay, so these are all significant. So let me actually just write this number. I don't want to do leading zeros yet. We haven't learned about it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 significant figures in this number. All of them are significant. Okay, zeros to the left. That means beginning zeros. So like 0.03120. These zeros right here are never significant. Leading zeros are never significant. Zeros in the front. So this number, these are not significant. Now they're important to be there. You need it there to tell you something about this number. That's a very small number, but it's really the 6 that's telling me the important information. Okay? So leading zeros are not important. Non-zeros are important, and zeros in the middle are also important, or significant. Finally, zeros to the right. So trailing zeros, this is trailing zeros, are sometimes important. Sometimes. So when are they important and when are they not? When there is a decimal point in the number, then they are significant. Decimal point means significant. Okay? So, for example, this number, 9.10. I have 3 significant figures. Okay? So why is it significant at this point? Well, I'm trying to tell you where the error is, where the uncertainty is. The uncertainty is plus or minus 0.01. This is the uncertain number. I'm certain about the 1, I'm just not certain about the 0. Okay? Why would I even write the 0? Isn't that the same as 9.1? Why don't I just write as 9.1? Who cares about the 0? Well, obviously I'm trying to tell you something important. This is where the error is. The error is at the 0.01, okay, at the 100th place. Okay, that's where the error is. So that's important. So that's why that 0 is significant after decimal. If I didn't have, let's say I had 3,000. Okay, let's say 30,000. Okay, There's only one significant figure here. That's the 3. These just have to be here because I have to tell you the number's approximately 30,000. But is it 30,000? Is it 2,000? I'm sorry, is it 30,000? Is it 20,000? Is it 40,000? This is the unknown. That's the uncertain value. These are not significant because I didn't put a decimal point. If I put a decimal point with a 0, now all of them are significant. Now I've got 1, 2, 3, 4, 5, 6 significant figures. Okay, so here's more information. There's a lot of information about oh, what is this? Zeros to the right of the list. Yeah, that's basically what we talked about. Okay, so for this number up here, take a second and determine how many significant figures are in that number. All right, you should have said there's 4. All right, leading zeros, not significant. Trailing zeros, as long as there's a decimal point, is significant. So non-zero, 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 trailing 0 with decimal point, 4 significant figures. Okay, so here's some problems. Put this on pause and determine how many significant figures. Welcome back. If you didn't leave, it's time for you to leave and then come back. Okay, so A, the answer, 3. All the numbers are significant. B, there's 4 significant figures. 0 in between numbers. C, leading zeros are not significant. The non-zeros are, so there's 3. D, there are 4. This is scientific notation, all right? But it doesn't matter. If there's a decimal point, all right, and there's 3 significant, and there's however many numbers after the decimal point, even though they're zeros, they're significant. Because why would I even write this? Why would I even write 3.00 times 10 to the negative 7? Why don't I just write 3 times 10 to the negative 7? Right? Why do I put all the zeros? Well, because I'm trying to tell you how much precision is inside that number. Okay? 50 milliliters. The answer is 1. Only the 5 is significant. Is it 50 milliliters? Is it 40 milliliters? Is it 60 milliliters? Okay. Finally, the last one, there's a leading 0 that is not significant. Trailing 0, only if there's a decimal point. There's a decimal point. Non-zeros are, so there is 4 significant figures. If you're a little confused and still having problems, that's okay. That's normal. This stuff really is, I mean, I'll be honest, is a little boring. But it's important when we start reporting numbers. It helps you determine how many numbers you have to use when you do calculations. Okay, so for example, if you get a number 4.7131258 out of your calculator, all right, you're not going to be reporting that whole thing. You're only going to be reporting the significant part of it. And if your 1 here is the uncertain value, then guess what? That's what your answer is. That's it, 4.71. That's how you report it. You show me where the uncertainty is. The rest of this has no certainty. All right, it's so uncertain because the number before it's uncertain. Okay, so what happens when you add and subtract these numbers or multiply and divide? All right, adding and subtracting is pretty straightforward. In addition to subtraction, the answer cannot have more digits after the decimal point than the original number with the smallest number of digits after the decimal point. All right, what does that say? Whichever one of these numbers has less numbers after the decimal point, that's how many have to be in your final answer. So this number has 2 numbers after the decimal point. This number has 3 numbers after the decimal point. Okay, so here's the full number. So how do you report it? Do you report the whole thing? No, you have to stop at this point right here because you stop whichever number has the least amount after the decimal point. So it's 2 digits after the decimal point, so that's where you stop. So you report the answer as 102.73 because 3 is the uncertain value. Okay, let's think about this. It's kind of obvious. Okay, so when I write these numbers down, these are measurements. Both these numbers are measurements. Okay. In this number, this is my uncertain value. That's uncertain. In this number, that's my uncertain value. So when I add these up, all right, if this number is uncertain, what does that tell me about this number? This number is also uncertain. All right, I'm positive about the 3, but I'm not sure about the 0. That might be a 1. So this might actually be 4. Or it might be a 9. So this might be a 2. Okay, this might be a 2, this might be a 5. I don't know what this is because I don't know what this is. So remember, when you report a number, it's got to have one uncertain value. So if this is the uncertain value because it's been added into it, then I can't report that number because then I would have two uncertain values. And that's basically the rule when you add and subtract. And then rounding, people always want to know about rounding. So here we'll go to here, the same number. Basically what you do is you only round your uncertain value with the one number before it. Okay, so look at the number before it. Excuse me one second, I gotta put this on pause. Sorry about that, I had a little bit of a coughing attack. All right, I'm better now. Okay, so where were we? Rounding, okay? The uncertain value is the only number that gets rounded, and you just look at the one number next to it. So since this is a 1, this stays a 3. If it's 5 or more, you round it up. Now, sometimes this happens, and let me show you what you do in this case. Okay, let's say I'm stopping it right here. Now, a lot of people, now this happens sometimes, and a lot of people start going a little too far. They see that there's a 9 here, which would round this 4 up to a 5, which would then round this 3 up to a 4, okay? You're pushing it way too far, okay? You just look at one number next to it. You ignore everything after it. So if there's like a 9, 9, 9, 9, 9, 9 here, I don't care. I don't care how many 9s there are. This stays a 4. Do not round this up based off of what's next to it so that you can round this up. Don't make this too complicated, all right? People tend to do this, okay? If this is a 4, then it stays a number. If it's a 5, then it's a, don't round this number. The only number you're rounding is this one, and it's based off of the number before it, okay? Multiplying and dividing now with the significant figures is pretty straightforward. It's different than adding and subtracting, okay? What you do is, in multiplying and division, the number of significant figures in the final product, all right, cannot have more significant figures than the original number with the smallest number of significant figures. Okay, so if we take this equation, which by the way, that is an error, that equal should not be there. This is 1.4 times 8.011. Okay, if you multiply this on your calculator, now the publisher gives me that. Let me see if it's more than that. I want to get exactly what your calculator says. Nope, that's exactly what it says. So 11.2154, that's what your calculator says, okay? Well, do I report all these numbers? Do I report some of it? Well, the rule is whichever one of these numbers has the least amount of sig figs, that's how many sig figs are in my final answer. So how many sig figs in 1.4? That is 2 sig figs. How many in 8.011? That is 4 sig figs. So my final answer has to have 2 significant figures. So here are the first 2. Okay, this is a 2, so I do not round, so my answer is 11. That's how you report the answer. You don't even include any of this stuff. Why is that? Because this has 2 uncertain values. That means the 1 is certain, but the 4 is not. So this number gets factored in to our final answer. Okay, so that means my uncertainty is right here at the second significant figure. So this number could be 12, it could be 13, it could be 10. I don't know, it's one of these because that uncertainty has been factored in based off of whichever number is the lowest. Okay, so that's what you do when multiply and divide. And then when you add and subtract. Now, when you have exact numbers, if you're multiplying and dividing exact numbers, the number of sig figs in the final answer is the amount of sig figs in your measurement, not in the exact. So this example says, how many grams of copper, is that what it's saying? How many grams of copper are in the pennies? No, a penny minted in 1982 has a mass of 2.8. If you have 3 such pennies, what's the total mass? Okay, so they're taking 3 and multiplying it by 2.5. Okay, now your 3 is an exact number. It's exact. All right, your 2.5 is a measurement because you had to weigh your pennies. So was it 2.5? Was it 2.4? Was it 2.6? Was it 2.3? Was it 2.7? Okay, so, and plus not every penny weighs 2.5 grams, does it? Maybe the penny that you weighed 2.5 grams, all right? But maybe you have another penny and it weighs 2.4 grams, and another one that weighs 2.6 grams, okay? So, technically your average is 2.5 in that case, but that's not the point, all right? The point is that not every penny weighs exact. This is totally averaging out the weight of our pennies. So, you don't use, so technically this is one sig fig, so you think, well, maybe the answer should be 8, right? Because it's one sig fig plus you round. Well, exact numbers don't have any bearing on it. It's your measured values. It's the measured value, okay? All right, multi-step rounding. This is just basically what I talked about. You only round the one number, don't round everything, okay? All right, I hope you understand sig figs. We'll do some problems in class, and I'll answer whatever questions you have. Hopefully by the time we meet and you watch these videos and I talk about it some more, you guys will understand sig figs. It's not a hard concept. It is a little tedious, I'll be honest, but it is kind of important. It just helps you determine how many numbers you have to put in your final answer.